Hi, math fans. I'm Dr. Andy Lovelace, longtime instructor at the University of Washington. I've been building towards this video, so if you haven't watched the previous ones, please watch my videos on history of Mariners batting averages, history of Major League Baseball batting averages, and then I talk a little bit about this thing of Farey sequences, really about fractions. This is actually a math video. I'm going to talk about why certain fractions are less likely than other fractions, but the application is batting averages, and I just think it's kind of interesting. But stick around. This is going to be a little bit longer than some of my videos because I want to do a recap of the question. I will do some theory, so this will be a little more, slightly more math heavy than some other things. We'll talk about why certain fractions are not possible, and then we'll try to predict which fractions are hard to find, which batting averages are hard to find in Major League Baseball. And then I'll finish with some practical stats. I have some visuals to show you. Okay, so let's get going right away. And then I probably won't be making that many videos after today because I'll start teaching my course. So it'll be 3D calculus visuals coming out for the next couple months. But keep bringing me your questions. Please put questions in the comments. Okay, recapping. Looking at baseball reference, I joined stathead.com, which has some great stuff. I just grabbed a few. The starting place was this, an observation I made long ago, because I've kept score books many times and scored games. But it's very unlikely to see a batting average of 332 and 334. That's probably not surprising. Many of you might have guessed that, and you might have a good reason already. But interesting little stats. If you look at every possible year-end batting average in Major League Baseball over the history of the game, 677 have batted 300. I just kind of picked that number. 57 have batted 332, which sort of makes sense because it's harder to bat 332, except for the fact that the next column is 1,552. Wow. And then you can't get very many 334. So things are not equally spread out when it comes to fractions. It's not just about baseball. It's about certain numbers can't happen. That's not going to matter to some people, but some people care a lot about baseball stats. I've been joking and saying, who's nerdier, baseball nerds or math nerds? What if you're both? Oh, no. Okay. Anyways, finishing the recap, and then I want to get to the theory. I don't want to waste too much time, wasting your time. Anyways, here we go. So I went to the Mariners stats. Now watch my previous videos where I actually go through some more realistic Mariners stats. But there are Mariners that finished the season batting 333. One of them was Felix Hernandez. He went 1 for 3. The only one that's sort of realistic is Carlos Guillen, but it was only 39 at bats. So you can see the problem with small number of at bats. As soon as you exclude it, there's not really any. But I wanted to use this as a data point. We don't have anyone that's batted 333. Sort of sad. Okay. There is no one in the Mariners organization that has finished a season at 332, no matter how you slice it. There's no one that has batted 334. There's no one that has batted 335 or 336. There is one person that's batted 331. Brett Boone did it in 2001. And that's a real number. An interesting thing is as you get higher, some of these become significantly more likely, but for low numbers, it's not. So I want to talk about that. Again, this video is about math. It's not about baseball, but I'm using this as a laboratory to talk about fractions and do some things that most people haven't seen about fractions. Okay. So going further, the next most difficult thing is around 250. And I'll talk about why that is, but there are 30 Mariners that batted 250. You can see a lot of those were, 1 for 4 or something. In fact, some of the numbers don't make sense. It's just, that's games played. I got it. But there are 8 that batted 249. So it's significantly less for 249. Ooh, one of them, Jeff Cirillo. He coaches baseball in this area. He used to coach against my brother. And then we have 251 is pretty rare too. Mike Zanino, but there's numbers in there. Okay. So we see the problem. If it's a problem, I don't know. But it's hard to bat some of these numbers. In particular, it seems to be hard to bet 249 and 334. And that leads to a discussion of fractions, which is the point of this. And something I saw long ago, I've never taught about this before, but it comes up in number theory, and it actually is valuable. And where I saw it was in proofs of why various things are irrational. It involved this discussion of how do we approximate with fractions. So there's some surprising consequences of this, but I thought, hey, here's a place that people might appreciate or understand where this comes up. If you restrict the number of at-bats to, say, 500 of at-bats, now, whether that's reasonable or not is a question. And when I looked at the Mariners stats, there's a lot of people that play a whole season that are between 300 and 500 at-bats. So I think a more realistic range is this range. But I've already done so much analysis. For year-end batting averages, that's kind of what you see. There are some people that come up towards the end of the season, so it'd kind of be interesting to study this range. What I will do at the end of this is I'll study the range 0 to 700, which is probably the more realistic, most realistic if I want to do the overall data. But let's just talk about this. These are the players that played every day. Usually on a team, there might be 2 or 3 or 4 of these guys. Some years, Mariners only had 2. Others, they had like 6 or 7. So there's a few guys like this. As soon as you're like that, things start to level off a little more, because with those denominators, you're more likely to get things balancing out. I think there still is some statistical suggestion here that this is harder, even in that range, but it's very slight, not convincing. Okay. So now I want to talk a little bit about why. I'm going to do like 3 different explanations of why. So first explanation that I think people would probably try on their own is just to start listing out, well, when do I actually get there? When do I get to that denominator? So I've done that here, and I've written down the first time we reach various batting averages, meaning after you round. And the hardest ones to get, the hardest one to get is a 1 batting average, and you will never see that in Major League Baseball for 2 reasons. One is you have to get to 667 at bats. That's the first time it happens. And 2 is if you have a team, an owner that keeps someone around who's has gotten 1 1 hit all season, that owner's going to be fired. Okay. Same thing with like 2, very unlikely. On the other end of 499 is very unlikely because you have to have 335 at bats. The first one that's somewhat reasonable is 334. You have to have 287 at bats. The next most challenging one to get is 249 because you have to get to 169 at bats. A lot of players never get there. I thought I'd be able to say that no one has ever batted 334 in the first half of the season, but I looked and there are a handful of people that did because once you get to 287 at bats, it starts to become more reasonable that it can happen. So there are a collection of players that have done it. All right. So that's sort of interesting. So let's take a peek here at where these numbers. So I highlighted the numbers that I thought were kind of in the reasonable range. Now, there are some people that have batted up to 440, but I'm going to focus on these numbers because you just don't have enough data to really look at that. All right. So I'm going to say a little bit about a few different things. I've already talked about the Farey sequence, but let's do it again. And this time, let's just talk about the numbers and watch my other videos on this between here and here. So 0.0, this is just a quick recap. This is 500, this is 0. And what I talked about is if you're talking about small denominators, meaning 3 at-bats, 4 at-bats, 5 at-bats, there is a way to build up your fractions, and it's typically something no one has ever seen. You add the numerators and add the denominators and construct a new fraction. So you do 0 plus 1, you add fractions in the wrong way. But that gives you the next fraction between them. It's called the median. Most people haven't seen that. That's 333. a really interesting thing about fractions is the moment you've placed a fraction in this Farey sequence, it's hard to get another fraction close to it. It takes a long time. It's really hard to approximate fractions with other fractions. It's a weird little quirk of the number system. It's actually easier to approximate irrational numbers with fractions than it is to approximate fractions with other fractions. It's a weird thing about how they're spread out. So anyways, if you keep going, the next one is 1 over 4. The next one is, over on this side, is 2 over 5. Again, adding the numerators and denominators. If you look at that, that's 0.250, and this is 0.400. And you should start to see that those are the numbers. Those numbers you can get, and they happen a lot. You know, you can go 1 for 3 or 2 for 6 or 3 for 9. So that happens a lot. But the numbers next to it don't happen very much. So if you go on either side of those, you're going to start to see these. Those are the problems. So if you keep going, let's see how many of these challenging batting averages happen. So what I did to help us with that discussion is I made a little spreadsheet. This is just me doing the Farey sequence here. So I have numerator and denominator, and we're just going to do it a few times. So I already did this one. Adding together, add the numerator and denominator, and then divide. So let me unhide what I tend to want to show you. And let's do this and move this over. Apologies. And we'll just keep going. So that's the first few. I've already noted that. That issue. Ignore the division by 0 piece. I'll fill that in a second. So let's kind of highlight as we go. So we already see that one of the problems is here. This actually extends further on either side because this number is so hard to get close to, and I'm going to give you another explanation of that in a moment. Again, I want to really just give this from a few different angles. I'm not trying to show you why it's miraculous. So those are why those are hard to get for most batters. You have to get, in the hundreds of at-bats. Let's keep going. Them add together. It's not that hard to 0 plus 1 is 1. 1 plus 3 is 4. So I'm adding the numerators. So that's 250. That's the next hardest to get. This is 2 and 5, 400. That's also hard to get. So if you look at either side of those, let's highlight the numbers next to 250. So that's these ones. Those are the ones that are challenging to get. And we see that when we look at the historical data. And these ones are challenging to get. So those are kind of the next most challenging. What are the next most challenging? All right, let's try it. 200, okay. 286, so that's kind of surprising. I wouldn't have thought that. 375, and then we're getting kind of bigger. These are just hard to get in general. So 200, yep, we see that. 200 right here, either side. Those are the reasons they're hard. That Farey sequence. I just thought that in itself is interesting. Here we have 285. Oftentimes on one side it's a little harder than the other because of rounding. For example, 3.3333 is closer to 3.334. That's why it's harder to get to 334 than it is to get to 332. But that's a different thing. 375. Okay, we see that. Let's go one more maybe. So one more. Let's go to the next level of the Farey sequence. So 1, 6. You're starting to see it's going to take a long time for us to get very close to 0 because you're going to get 1/7, 1/8. That's a hard number to get close to in terms of small denominators. And that's what we're talking about here. So if you've never realized this, if you're trying to approximate something with small denominators, there's this clever little thing where you just add the pieces together. So there's that 300 coming up. So 301 is hard to get. Some of the numbers I only put in the, things that you had to go out to like 70 or 80 to get your first example. So here's this 272 is hard to get, 222, 166, done it. So basically those are all the numbers up to whatever I was, the third or fourth term of the Farey sequence. And all of those require you have at least 90 to 100 at bats. So that's kind of interesting. That collection of batting averages is going to be pretty rare. just simply because there's so many batters that have so few at bats in a season. So I think, like I said, baseball people love random facts. That seems pretty random. If you want to think about it another way, you can think about it in terms of continued fractions, which has a strong connection with the Farey sequence. I did that in a previous video. If you look at the continued fractions for these numbers, what I found in one paper, I was like, has anybody asked this before? And I found one paper where someone talked about the continued fractions of the numbers halfway between these. So they looked at like 0.3345. They actually didn't look at 0.334. I'm surprised. I haven't found anybody that's written about this 334 phenomenon. But the continued fraction of those, certain ones you can't approximate really well. That's another way to say what we're seeing in the Farey sequence. What I can really tell you is when I first happened upon this and was thinking of this problem, what I thought was, okay, I see this phenomenon with 334, and so then I started to just try to approximate it. And so I was like, okay, I don't need to worry about any of these other things. Let's just grab this. And so I said, all right, here's 1/3, and I need to just keep working my way down closer and closer until I get to this number. And I realized it was going to take forever, because you add 1 to the top, so it's going to be 2. You add 3 to the bottom, it's going to be 5. Add 1 to the top, add 3 to the bottom. Add 1 to the top, add 3 to the bottom. This is pretty cool if you've never seen this. Add 1 to the top, add 3 to the bottom. Add 1 to the top, add 3 to the bottom. These are each getting closer and closer to 1/3, and it's the best you can do. And so to me, that really shows you why it's going to take a long time, because you're not going to get there till you get to 96 over 287. That's the first time you're going to round to 334. That's also why it's hard to get close to 335 and 336. All right, let me give you some other visuals of this, which I really like. This is from Wikipedia, but it's such a good visual. So you can see when you place these first two numbers, they're really far away, and then it's hard to get close to them because of this adding fractions and getting further and further out. So if you go to the next one, there's the next fractions you place. You can see these big gaps that start to form around the numbers. It's hard to get close. When you lay down the next ones, they're a long ways away from 0 and 1. When you lay down the next ones, they're pretty far away from 0 and 1, but they're also far away from a half. Those are the biggest gaps. The biggest gaps are near 0 and 1 and near a half. Then the next one, the biggest gaps are between 0 and 1, a half, and then a third. So you can see this, how it's hard to get close. What we were just observing, let's go to this lowest level that it shows. Let me move my mouse out of the way. What you're seeing here, it keeps trying to do that, is it's hard to get close to a third. So there you go. Particularly 0.334. My visual I made for this, and sorry if this is getting too long, was this. I think this is pretty compelling. So what I did is I put every fraction that you ever get with any denominator, and then if it happened again, I put a little green dot above it, and I kept putting those up. Looks like so this is up to the first 40 denominators. So this doesn't even get close to getting to 344. But you can see, we're going to zoom in. So you can see there's a big gap. It takes a long time to get close to a half. Let's zoom in there. I'm just having it keep entering these numbers as we go. But let's go over to 0.3, and it's like you just can't get close enough. There's 0.33. So 0.334 is really close, and it's going to take forever to get there. These dots are just taking too long. And then we're going to see this same phenomenon. You can see it when you zoom out. There's just nothing close there. And there's nothing close to 0.25. It's this weird behavior that when you're approximating with small denominators, it takes a long time to get close to those first few numbers you placed. Okay, I just thought that's pretty cool or surprising that not very many people know this fact. Okay, lastly, let's look at some counting and some statistics. So I was then, okay, is there a practical piece to this? Probably not. And I'm very applied in most things I teach. Don't let this give you the wrong impression. But it is opening day tomorrow, and I'm going to be at the Mariners game. So I thought, let's talk about this a little bit. Okay, so here's just a practical explanation. If you wanted to bat 333, you can do that right away. Go 1 for 3, and then 2 for 6, and then 3 for 9. And these are what you get all the way up to here. Every basically third at bat, you could be batting 333. 334 is not going to happen until you get to 287 at bats. So it makes sense that, so definitely for your first 200 at bats, it's impossible. For your first 286 at bats, it's impossible to bat 334. Okay. And so in a sense, it's the hardest average to have in Major League Baseball. That's not quite true. I shouldn't say it that way. If you allow denominators, the moment you get to 300, it does happen. But I did a little bit of a counting argument. I basically looked at all the fractions that are possible, and then I looked at those fractions that were equal to 0.33, and I divided by the number ones that were 0.34, and there's 94% more fractions that are 0.33. So it's still more likely if you're batting around that point that you're going to bat 0.33 if you're batting between 300 and 400 bats. Between 500 and 600 bats, it shrinks a little bit. It's about 60% more likely if you're around here that you're batting 333 as opposed to 334, just because there's more fractions. You get this kind of doubling effect that every third one is 0.33, as well as these other ones that are nearby that happened around. Interesting, the moment you go from 600 to 700, they equal out. There's the same number that round to 334, and pretty much after that, it's pretty evenly spread out. So that's sort of interesting. Now, when you look at year-end stats, it usually includes everyone, and most people are between 100 and 600 at bats. So actually, this is probably a little different. But I did 0 to 700, which pretty much includes everyone except Ichiro, Helton, and 2 other people historically. So this pretty much takes care of everybody. And if you count the fractions, among all the fractions, there's 17% more 250s than there are 249s. So it's still slightly more likely among the fractions. When you look at 333, it is significantly more likely to have 333 than 334 if you consider all the fractions between 0 and 700. Now, a lot of the players, the data isn't quite as striking when I actually look at it, but I am going to pull up something here to show you. So this is just data I collected. This is all the Major League Baseball batting averages end of season for people batting more than 100 at bats. So I should have included everything, I realize now when I look at this, but you do see these gaps, these small bumps are going to be at those, similar to those same numbers we saw, where you get these anomalies where there's a lot at 300, but there's very few at 299. You can now have a reason for that. These little anomalies where 275, was that one of our numbers? No, it wasn't. It's close to one of them. You get this big bump here at 250. And 249 is really low. So you can explain that now. It just has to do with fractions. It's not because it's easier to bat to. It's just a fraction quirk. All right, let's finish looking at some graphs here I've put together. So this is every possible batting average up to 100 at bats. You can see that there's nobody that can bat a 334, and you see these sort of irregularities, these little dips, these random spots in the middle. If you look up to 200 at bats, you still see this kind of unusual thing around this 334. There's also a problem around 250. If you then go to 200 to 300 at bats, you can still see there are a few cases where people bat 334, but not very many. If you look at 300 to 400, 500 to 600, now when you go up, you see it starts to level off. That's if everyone batted between 6 and 700 at bats, though, and very few players do. And so if you put it all together, up to 700 bats, you still have a pretty big statistical difference between the likelihood of those fractions. So that's pretty interesting. Okay, finally, let's end with a look at baseball reference here. This is every person. So as I said initially, if you don't give any qualifications and you just say number of at-bats, there's about 1,500 people that have batted 333 in Major League Baseball history. There's a total of 43 that have batted 334. So these are the rare cases. Only 43 people ever have batted 334. Derek Jeter did it. Of course he did it. Yet another accolade that he probably doesn't care about. But not that easy to bat 334. He had 634 at-bats. Again, once you get that many at-bats, it's about as equally likely as other things. Goose Goslin, some names you might know here. Adrian Beltre did it, had 598 at-bats. Lou Gehrig did it. Home Run Baker. Love that name. Jeff Kent. Goose Goslin again? Oh, man, look at that. How many people have batted 334 twice? David Segui. Let's keep looking at these. Pudge Rodriguez. Sock Saybold. Ty Cobb, of course. He's in every single stat. So there you go. Now, some of these, as you see, this is about as low as you can go. The reason there aren't a whole bunch more is because the smallest number of at-bats you can have is, what did we say, 287? Cool Papa Bell. Love that. All right. So anyways, interesting note is that Goose Goslin batted 334 twice. Pretty spectacular. So I don't know if he even knows that fact. If anybody knows Goose Goslin, tell him I'm impressed. He batted 334 twice. It is hard to bat 334 because of fractions. All right, hope that was interesting. I know that was probably too long, but I'm going to get back to my own classes. Probably won't have as many videos, but I would still like to get your comments, your questions, so that maybe this summer I can return to some baseball math. All right, thanks.